Let us now start with the design of control systems. So we know that a control system, very initially we've discussed, it is a system which is an interconnection of various components in order to perform a specific objective, right? If you consider the washing machine, there is a control panel on the washing machine, right? So if you press each of the button, if you say wash, then it has to wash. If you say it has to dry, then it will dry the clothes, right? So these are all the specific objectives. Now what are the specifications? The specifications are the parameters which need to be followed so that this objective that we have, it is performed satisfactorily. Okay. Now when we design a control system, we need to develop a control system which is satisfying certain specifications, technical specifications, whatever we have discussed in the time domain or frequency domain. It has to be stable, or it has to have this much amount of overshoot, okay, or it has to be this much speed, right? So these are all the specifications. Now we will not go through with the entire design process in depth, but just a basic idea of what is meant by design, okay? And one important thing to remember is design is never a straightforward process. So that means it's not like logic 1 plus 2 is equal to 3. It's never a straightforward process, okay? So this is the most important thing you have to remember. Only when you do it in a trial and error basis, you're going to get the most satisfactory result. We will now start with the discussion of different types of controllers, alright? So usually for a control system, there will be a plant transfer function. If you take the example of the fan, we can control the voltage that is given to the fan by means of a regulator, thereby controlling the speed of the fan, right? So now if you consider this to be the controller and this to be the actual fan, then this controller is adjusting a parameter of the fan, which is speed in this case, right? So this is a basic example. In control systems, we have different types of controllers, which is what we will be discussing now. The first controller is the proportional derivative controller. So this is abbreviated as PD controller. So how does it look like? What is the transfer function and what are the effects of this kind of controller? So first you will have the plant transfer function in the forward path, right? And you're going to have the feedback transfer function as well, which we will represent as h of s, okay? Now in the forward path only, you're going to have the PD controller. It will have two parts. One is the proportional part, which is nothing but it is a constant. The transfer function is a constant, okay? And there will also be a derivative. What is the transfer function of a derivative? It is s, and we will use a constant as well, okay? Kd is the constant. So now this entire part here, this is called as the PD controller. Where is the input? This is the input and this is the output. So the transfer function of the PD controller is given by Kp into Kds, okay? So this you can write as Kp into 1 plus Kd by Kp into s. That is the time constant form. 1 plus Ts. If you write, this is the time constant form. So you can see here that the PD controller has a 0 at s is equal to minus Kp by Kd. Does it have any poles? No, it doesn't have any pole. Now what are the effects of the PD controller, right? So the very first effect is the speed of response is increased. So why is that? If you can see in the transfer function, you have the error function here, right? This is the error function and you can write it as E of S, right? Now error function is being multiplied with a constant here, which is the proportional part, and here with the derivative. Okay, so that means the system is not only responding to the error function but also to the rate of change of the error function, which is what will increase the speed. That means the system is anticipating. For example, if you take, let us say the error is at this point. This is the time and this is the error function. Okay, so now the system is responding to the error function. But in addition, it is also responding to the rate of change. That means in the future, is it increasing or decreasing, or is it remaining constant? It is able to anticipate. The system is able to anticipate. So as a consequence, the speed will be improved because it is able to anticipate what is the kind of effect that is coming, and accordingly it will respond. So that is how the speed of the system is going, speed of the response is going to change. Okay, so you can write here, faster response is achieved. Next, the second point is the transient response. It is going to improve. Improved transient response. So what is the transient part? The part which will die out after some time. For example, you have seen in time domain specifications, if this is the final output, then there will be some oscillations before finally settling down. Okay. Now wherever till the point of oscillations, we call it the transient part. Now the transient part will depend on where the poles will lie. If you remember, the dominant poles were closer to the j omega axis. If the pole is much farther away from j omega axis, it will not have much effect. Okay. So now if you want to suppress the effect of this dominant pole, then if you keep a 0 here, then you can suppress the effect of this dominant pole, right? So now the PD controller is nothing but a 0, right? So in such a way, if you place the 0 appropriately near to the pole that we wish to suppress, then it will improve the transient response. Okay, so this point is important here. There should be, the 0 should be properly placed, then only transient response will improve. Okay, so the next effect is, it has a high pass characteristic. Okay, so what is meant by a high pass characteristic? It will allow only the higher frequencies to pass. The lower frequencies, it will not give a satisfactory output. Okay, so this you can understand if you look at the Bode plot. So how does the Bode plot of a 0 look like? It is going to be like this. This is the magnitude plot. What about the phase plot? The phase plot is going to look something like this. It is going to start at 0 degrees and it will end at 90 degrees. So now we know that output is equal to the transfer function into input, right? Now here the transfer function below a certain frequency, it is nearly 0. So if transfer function is 0, then output will not be present. So only after a certain range of frequencies, a certain value of frequency, the magnitude is not 0, right? So only those frequencies will be passed. That is why we call it as a high pass filter. It has a high pass characteristic. Next, this kind of controller, it will increase the bandwidth. So bandwidth, you can visualize, it has number of definitions, but one way in which you can visualize is the range of frequencies for which the controller will operate. Okay, so now the bandwidth, when it increases, what will happen to the rise time? The rise time is inversely proportional to the bandwidth. So that is going to reduce. Okay, so that means you have a faster response time. That is what we have seen in the first effect. Speed of response is fast. Now one negative effect that you have is that the high frequency noise will be present. High frequency noise will be present. Okay. Next, another important effect is the increase in stability, improved stability. So you can see from the phase plot here that there will be an additional phase, positive phase, that is being added because of the PD controller. So you can write PD controller increases the overall phase of the open loop transfer function. So this means that the phase margin, which is what, 180 plus the phase, at what frequency? At the gain crossover frequency. That means when the magnitude crosses 1, or in dB if you take it as 0 dB. So if this is going to increase, then phase margin will increase. When phase margin increases, then you can say that it will improve the stability. Okay. So these are the various effects of a proportional derivative controller, or what you say is PD controller. Next we have proportional integral controller. So this is abbreviated as PI. Here you are going to have a proportional as well as an integrator block, right? So there is a planned transfer function in the forward path. Here you have the output. Here you have the feedback path. This is going to get added here along with the input. Input is compared with the feedback signal. Okay. So here you have a controller, proportional controller. So this we can take as some Kp, and also parallelly we have the integrator. So you can take this as some Ki by S. Both will be added. Okay. So now this entire thing here, it will form the PI controller. What is the transfer function of controller only, not the entire transfer function? This is Kp plus Ki by S. So what you have here, you can rewrite this as S into Kp plus Ki divided by S. So what does this mean? It means that there is a 0 and also a pole which is at origin. The 0 is not at origin. We have 0 at S is equal to minus Ki by Kp at non-zero point, but the pole is at origin. So now what will be the effect of a PI controller? What are the various characteristics? So the very first characteristic is that it will improve the steady state response. In PD controller we saw it improved the transient state response. This is going to improve the steady state response. What will happen when you increase the type of a system? For type 0, type 1 we have discussed, right, in time domain analysis. So there we have seen that as the type increases, the error is going to reduce. Okay. So that is why here we have a pole at origin which is going to increase the type of the system, and that is why it is going to eliminate the error. Okay. So you can write here, error can be eliminated by increasing system type. So that is why PI controller will improve the steady state response. Okay. Next, this has a low pass characteristic. Previously for a PD controller we had a high pass characteristic. Here it is going to be low pass, and this you can understand if you see the Bode plot once again. So here the Bode plot is the addition of the pole at 0 as well as the 0 at a non-zero location. Okay. So you should add both of them. So the pole at 0, Bode plot is going to be like this. We are talking about the magnitudes first, plus what about the Bode plot of 0? It is going to be just like in the previous case, it is going to be like this. So now if you combine these two, then you are going to get a Bode plot which is somewhat similar to this. Okay, so this is the magnitude Bode plot of the PI controller. Then what about the phase Bode plot? The phase Bode plot is going to be somewhat like this. It is going to start at minus 90 degrees and it is going to increase to 0 degrees. So that means there is a negative phase. It is contributing a negative phase. From the magnitude plot you can see that it is allowing only the low frequency signals. If it is higher frequency, then the transfer function is effectively becoming 0. So the higher frequencies will not be passing. That is why it has a low pass characteristic. Okay. Next, what will happen to the bandwidth? The bandwidth is going to reduce because of the low pass characteristics. Now once bandwidth is reducing, then what will happen to the rise time? Rise time is inversely proportional to the bandwidth, so if it decreases, then rise time will increase. So that means the speed of the response will be affected. Okay. Next, what about the high frequency noise? So the noise is usually of high frequency. That's why we are talking about the high frequency noise. Okay. So high frequency noise will be filtered out since the noise is usually of high frequency, but this is a low pass characteristic, so the high frequency noise will be filtered out. So these are a few effects of the PI controller. And finally we have the PID controller. So that means there will be both integral as well as derivative blocks. Okay. So in that case, what will be the transfer function? If you see the block diagram, then it is going to have a proportional block, a derivative and a integral controller. Okay. So all of them will be added. Okay. So this will form the controller. So I am not drawing the entire transfer function, only the controller I am drawing. So this forms the PID controller. All of this will be added. Now what will be the transfer function? This is given by Kp plus Kds plus Ki by S. Okay. So what are the effects of the PID controller? So this will have, we can choose the values of this Kp, Kd and Ki in a proper way so that we can get the best out of PI as well as PD controllers. Okay. By choosing proper values of Kp, Kd and Ki, we can get the best of PD and PI controllers. Okay. Now what about the high pass low pass characteristic? Here we can either get a band pass possibilities, you can write. What will be the transfer function of band pass? It will allow a certain band of frequencies. So that is why it is called band pass. What is the other kind? We have band reject. So that means it will reject a certain range of frequencies. It will allow all other frequencies apart from that range of frequencies. Okay. So both these possibilities it is possible by choosing the proper values of Kp, Kd and Ki. Okay. So you can write a sort of summary of differences between the effects that you see in a PD and PI controller. Okay. So it will be easy to visualize that way. So we will take the PD controller on one side and PI controller on one side. Okay. So the very first is the speed of response. In a PD controller we saw that the faster response is achieved. Okay. The rise time TR is reduced. In a PI controller, the opposite is going to happen. The rise time is going to increase. So that means there is a slower response. Next, in PD controller, the transient response is improved. Transient response is improved. In a PI controller, what is improved? The steady state response is improved. Next, what about the bandwidth? Here, bandwidth is going to increase because of the high pass characteristics, and here bandwidth is going to reduce. Another consequence of the high pass and low pass characteristics is the filtering out of high frequency noise. So here we have presence of high frequency noise because of the high pass characteristics. Whereas for a PI controller, what is going to happen? The high frequency noise will be filtered out because of the low pass characteristics. Next, what about stability? Here we have improved stability, but in the case of PI, the stability will be reduced, but by choosing the proper values, we can make sure that stability is not much affected. Okay, we can design in such a way that stability is not affected. That is the existing stability, whatever the existing stability condition is there before you put the PI in PI controller, that we can ensure that it is not disturbed. Okay, you cannot, it's not really that easy to improve stability in PI.